The year 2026 represents a convergence of cosmic dangers that NASA's engineers and scientists are monitoring with increasing concern. While humanity celebrates its expansion into space, launching satellites, planning lunar bases, and preparing Mars missions, the environment beyond our atmosphere grows more hostile by the day. Some of these threats emerge from natural cosmic forces that have existed since the formation of the solar system. Others are entirely of our own making, byproducts of decades of space exploration without adequate foresight. Together, they represent challenges that could reshape or even halt humanity's reach into the cosmos. These are the 5 space threats NASA cannot afford to ignore in 2026. Threat 1. The invisible storm from the Sun. The Sun entered solar maximum in 2024, and this peak period of activity will continue throughout 2026. During these years, our nearest star transforms from a relatively calm sphere of hydrogen into a churning dynamo of magnetic chaos. Sunspots multiply across its surface, some spanning distances larger than Jupiter. From these dark magnetic disturbances emerge solar flares and coronal mass ejections, violent eruptions that hurl billions of tons of charged particles into space at velocities approaching 3,000 kilometers per second. The predictions made years ago have proven conservative. Solar Cycle 25, initially forecast to be relatively weak, has exceeded expectations with sunspot counts climbing past 150 per month during peak periods. Throughout 2025 and into 2026, the Sun has unleashed X-class flares, powerful enough to cause radio blackouts lasting 30 to 60 minutes across entire continents. In November 2025, a particularly severe geomagnetic storm struck Earth, registering as a G4 event and causing multiple spacecraft to report transient memory errors and temporary malfunctions. The May 2024 event provided a stark preview of what 2026 might bring. A barrage of solar flares and coronal mass ejections created the strongest geomagnetic storm Earth had experienced in 2 decades, generating auroras visible as far south as Mexico and causing power grid fluctuations across northern Europe and North America. For weeks afterward, NASA worked to assess the impacts on satellites and the International Space Station, documenting dozens of anomalies and adjusting protocols for future events. When a coronal mass ejection strikes Earth's magnetosphere, the planet's magnetic field channels that energy into the upper atmosphere, creating geomagnetically induced currents that can flow through power lines, pipelines, and telecommunications cables. These currents aren't subtle pulses. They can reach 100 amperes or more, capable of overloading transformers and replicating regional blackouts like the one that plunged Quebec into darkness in March 1989. In that event, 6 million people lost power for 9 hours, and some transformers suffered permanent damage requiring months to replace. Satellites face even greater dangers. The International Space Station conducts emergency maneuvers several times per year to avoid debris, but solar storms present a different challenge. Energetic particles bombard the station's hull, irradiating electronics and posing health risks to astronauts. During severe storms, crew members must shelter in the most protected sections of the station, postponing spacewalks and waiting for conditions to improve. For the thousands of satellites in low Earth orbit, particularly the megaconstellations operating at altitudes between 500 and 600 kilometers, solar storms cause atmospheric expansion that increases drag and accelerates orbital decay by up to 20%. Some scientists warn that 2026 could witness a Carrington event-scale storm, named after the 1859 geomagnetic storm that set telegraph systems ablaze and produced auroras bright enough that people thought the sun had risen at midnight. In our electrically dependent civilization, such an event would be catastrophic. Estimates suggest a modern Carrington event could cause power outages lasting weeks or months, disrupt satellite communications globally, and result in economic damages exceeding several $1 trillion. NASA's Space Weather Prediction Center operates around the clock, monitoring solar activity and issuing warnings, but the lead time for coronal mass ejection impacts remains frustratingly short, typically just 12 to 72 hours. Threat 2. Rocks from the void. Every asteroid that crosses Earth's path represents a cosmic lottery ticket we didn't ask to purchase. NASA's Planetary Defense Coordination Office tracks more than 2,493 potentially hazardous asteroids, defined as space rocks larger than 140 meters that pass within 4.6 million miles of Earth's orbit. While that distance sounds vast, in astronomical terms, it's barely a whisper, and orbital mechanics can shift these trajectories in unpredictable ways over decades and centuries. The early weeks of 2025 provided a sobering reminder of how quickly asteroid threats can materialize. On December 27, 2024, the Atlas telescope system in Chile detected a new asteroid designated 2024 YR4, measuring between 40 and 100 meters wide. Within days, automated systems flagged this object with alarming news. It possessed a measurable probability of striking Earth on December 22, 2032. By late January, that probability had crystallized into concrete numbers. Asteroid 2024 YR4 achieved a rating of 3 on the Torino Impact Hazard Scale, and at its peak assessment carried a 3.1% chance of collision, the highest impact probability NASA had ever recorded for an object of comparable size. Telescopes around the globe mobilized to track 2024 YR4's trajectory. The Magdalena Ridge Observatory in New Mexico, the Very Large Telescope in Chile, and dozens of other facilities turned their instruments toward this tumbling fragment of rock. Each observation refined the orbital calculations, slowly painting a clearer picture. By early March 2025, enough data had accumulated to ease fears. The asteroid posed no significant impact risk after all, but the episode revealed critical vulnerabilities in our detection and response systems. The asteroid was discovered less than a month before it topped risk assessment lists, leaving minimal time for detailed characterization. If 2024 YR4 had maintained a significant impact probability, the limited observation window before it moved beyond range would have left dangerous uncertainties about its composition, structure, and exact trajectory. These details matter enormously for deflection planning. The International Asteroid Warning Network issued its first-ever potential asteroid impact notification during this event, demonstrating that planetary defense protocols actually function when tested, but also exposing how thin the margins truly are. Smaller asteroids present even greater challenges. Objects in the 20 to 50 meter range, comparable to the Chelyabinsk meteor that injured 1,600 people in Russia in 2013, remain largely invisible to current detection systems until they're already upon us. These rocks approach from the direction of the sun, hidden in its glare, giving zero advance warning. The Chelyabinsk impactor exploded with the force of 30 Hiroshima bombs, shattering windows across 6 cities and sending thousands to hospitals with lacerations from flying glass. It was pure chance that the blast occurred over sparsely populated terrain rather than a major metropolitan area. Next time, we might not be so fortunate. NASA's NEO Surveyor mission, an infrared space telescope specifically designed to detect asteroids approaching from the sun's direction, remains years away from launch, currently scheduled for late 2027. Until then, a significant blind spot persists in our planetary defense capabilities. We're watching for threats coming from the night side of Earth while the day side remains unmonitored, a cosmic version of locking the front door while leaving the back door wide open. Threat 3. The Cascade. Waiting to happen, more than 36,000 pieces of tracked debris larger than 10 centimeters orbit Earth, remnants of decades of space activity. Each fragment travels at velocities up to 28,000 kilometers per hour, fast enough that even a paint fleck carries the kinetic energy of a bowling ball dropped from a skyscraper. These objects crisscross the orbital environment in thousands of different trajectories, creating a three-dimensional minefield that grows denser every year. The Kessler syndrome, proposed by NASA scientist Donald Kessler in 1978, describes a tipping point where orbital debris becomes so dense that collisions generate more debris faster than natural processes can clear it away. Each collision produces thousands of new fragments, exponentially increasing the risk of subsequent impacts in a self-reinforcing cascade. Some modeling results suggest certain orbital regions have already crossed this Threshold, meaning debris populations will continue growing even if all launches stop tomorrow. As of 2025, there are approximately 11,800 satellites in orbit, a number dominated by a single system. SpaceX's Starlink constellation accounts for 7,135 of these satellites, more than 60% of all active spacecraft. Between December 2024 and May 2025, Starlink satellites performed 144,404 collision avoidance maneuvers, an average of one maneuver every couple of minutes, day and night, for 6 months straight. That represents 3 times the rate of the previous 6-month period, illustrating how rapidly the collision risk environment is deteriorating. The International Space Station has conducted emergency debris avoidance maneuvers more than 30 times in the past decade. In November 2024, the station performed 2 such maneuvers within a 6-day period, forcing astronauts to take shelter in escape vehicles as tracked debris passed uncomfortably close. In April 2025, another close approach required similar precautions. Each incident underscores a troubling reality. The window of time available to avoid catastrophic collisions is shrinking. Recent calculations suggest that what used to be 164 days of advance warning in 2018 had collapsed to just 5.5 days by June 2025. A 2025 analysis revealed another disturbing possibility. A severe solar storm could knock out satellites' ability to receive avoidance commands long enough that collisions become inevitable, potentially triggering a Kessler syndrome cascade. The analysis suggested less than 3 days would be available to take protective action once a major geomagnetic storm began affecting satellite operations. During solar maximum in 2026, when space weather events occur with higher frequency and intensity, this scenario moves from theoretical to genuinely possible. The European Space Agency's Clear Space 1 mission, scheduled for 2026, aims to demonstrate active debris removal technology by capturing and deorbiting a defunct payload adapter. Japan's ELSA-D mission and other efforts represent steps towards solving the debris problem, but they remain experimental demonstrations rather than operational systems. The scale of the challenge vastly exceeds current capabilities. With hundreds of thousands of debris fragments too small to track but large enough to destroy satellites, and with new launches adding to the congestion daily, the orbital environment approaches a crisis point that technology alone may not resolve without international cooperation and binding regulations. Threat 4. The Mega-Constellation Collision Clock. The rapid deployment of satellite megaconstellations has fundamentally transformed Earth's orbital environment in just 6 years. When SpaceX launched the first Starlink satellites in May 2019, barely 2,000 active satellites circled the planet. By the end of 2025, that number exceeded 11,000, with most of the increase coming from Starlink. Amazon's Project Kuiper adds another dimension to this transformation, with the company racing to launch 1,600 satellites by July 2026 to meet regulatory deadlines and 3,200 by July 2029. China's growing constellation ambitions compound the challenge. The Qianfan constellation already has 72 satellites aloft, with plans to eventually reach 14,000. Other nations and companies announce similar mega-constellation proposals with disturbing frequency. If current trends continue, experts predict the rate of collision events could double by 2026, and collision avoidance maneuvers might reach tens or even hundreds of millions per year across all satellites. The Collision Realization and Significant Harm Clock, developed by researchers at the University of British Columbia, quantifies this threat using statistics to estimate how long spacecraft have to avoid dangerous close passes. The clock value has collapsed from 164 days in January 2018 to approximately 5.5 days as of June 2025. The average satellite in low Earth orbit now faces a 17% chance of a close approach within 24 hours that could lead to a collision, necessitating constant automated maneuvers to maintain safe operations. Coordination between operators remains ad hoc and voluntary, with no binding international standards for collision avoidance. Starlink satellites use automated systems that fire thrusters when collision risks exceed certain thresholds, but questions persist about whether these systems can scale to handle encounters with multiple competing mega-constellations, each employing different avoidance algorithms. A recent incident where a Starlink satellite nearly collided with a European science satellite due to a bug in the communication system demonstrates how fragile these coordination mechanisms remain. NASA expressed concerns in a letter to the Federal Communications Commission about whether automated collision avoidance systems will function properly at scale, pushing back against SpaceX's claim of zero risk. For active Starlink satellites, the agency particularly worried about failed satellites that lose maneuverability and become uncontrollable hazards, and how mega-constellation avoidance systems would interact with separate constellations employing their own unique protocols. The consequences of a major collision between mega-constellation satellites would extend far beyond the immediate destruction. The resulting debris cloud, with orbital parameters initially unknown and difficult to measure, could threaten thousands of other satellites in similar orbits. Modeling suggests that within just 15 minutes of a collision generating a short-term debris cloud, the collision probability with nearby mission satellites could exceed the red warning threshold. As time extends, that probability climbs rapidly, potentially triggering secondary collisions that cascade into the very Kessler syndrome scenario scientists have warned about for decades. Threat 5. The invisible enemy beyond Earth's shield. Beyond Earth's protective magnetic field and atmosphere, galactic cosmic rays pose an insidious threat to astronauts venturing into deep space. These high-energy particles, accelerated by supernova shock waves to velocities approaching light speed, consist of every element in the periodic table stripped of electrons and traveling as bare nuclei. Unlike solar particle events that arrive in discrete bursts, galactic cosmic rays bombard spacecraft constantly, penetrating hulls and human tissue with ease. NASA's Artemis program plans to return astronauts to the Moon in the coming years, with crews facing radiation exposures dramatically higher than those experienced aboard the International Space Station. While ISS astronauts receive approximately 72 millisieverts during 6-month missions, protected by Earth's magnetic field, which still extends partially to the station's orbit, lunar missions will expose crews to the full brunt of galactic cosmic radiation. Future Mars missions present even greater challenges, with round trips potentially lasting 3 years and cumulative radiation doses exceeding 1,000 millisieverts. The biological effects of galactic cosmic rays differ fundamentally from familiar radiation sources like X-rays or gamma rays. Heavy charged particles, particularly iron and silicon nuclei, create dense tracks of ionization as they pass through tissue, causing complex DNA damage that cells struggle to repair. Studies on mice exposed to simulated cosmic radiation reveal disturbing effects: impaired neural circuits, diminished cognitive function, problems with learning and memory, and increased anxiety. If these results translate to humans, astronauts on deep space missions could experience degraded decision-making abilities and difficulty responding to unexpected situations precisely when those capabilities matter most. Research at NASA's Space Radiation Laboratory using particle accelerators to simulate cosmic ray exposure has provided crucial data, but significant uncertainties remain. The accelerators can only expose subjects to one type of particle at a time, while real cosmic radiation consists of multiple particle types acting simultaneously in complex combinations. Scientists have proposed building multi-beam accelerators capable of generating several particle streams with different characteristics at once, but such facilities exist only as concepts on paper. Shielding astronauts from galactic cosmic rays presents extraordinary engineering challenges. Materials rich in hydrogen, such as polyethylene or hydrogels, can slow charged particles, but their effectiveness remains limited. Particularly energetic galactic rays penetrate even thick shielding, sometimes generating secondary radiation that increases the total dose. For a Mars mission, adding enough shielding to substantially reduce cosmic ray exposure could increase spacecraft mass by thousands of kilograms, exceeding launch constraints and costing millions of dollars. Timing missions to coincide with solar maximum provides a partial solution. During peak solar activity, the Sun's enhanced magnetic field and increased solar wind partially deflect galactic cosmic rays, reducing their flux within the solar system. But this strategy creates a cruel irony. Launching during solar maximum to minimize cosmic ray exposure increases the risk of encountering dangerous solar particle events, which during major flares can deliver lethal radiation doses within hours. NASA's research focuses on three complementary approaches: improving physical shielding materials, developing pharmaceutical countermeasures that enhance cellular repair mechanisms, and designing mission profiles that minimize time spent in deep space. Dietary supplements, antioxidants, and anti-inflammatory drugs show promise in laboratory studies for reducing radiation damage, but translating these results to actual mission conditions remains uncertain. The agency applies the ALARA principle, keeping radiation exposure as low as reasonably achievable, but for multi-year Mars missions, reasonably achievable may still result in unacceptable health risks. The radiation challenge extends beyond physical effects to psychological ones. Astronauts selected for deep space missions will need to accept significantly elevated cancer risks, potential cognitive degradation, and possible cardiovascular problems years or decades after their return. They will venture beyond humanity's protective cocoon into an environment fundamentally hostile to biological life, armed with incomplete understanding of the dangers and imperfect countermeasures against them. The convergence. These five threats do not exist in isolation. They intersect and amplify each other in ways that compound the dangers. Solar storms during maximum activity can disable satellites' collision avoidance systems precisely when megaconstellations create record numbers of close approaches, potentially triggering Kessler syndrome cascades. Asteroid deflection missions require years of preparation time, but our detection capabilities provide only months or weeks of warning for some objects. Cosmic radiation threatens astronauts on missions to establish lunar bases and Mars colonies, but debris-filled orbital environments may eventually prevent spacecraft from safely reaching those destinations. The 2026 timeframe places all these threats at or near their peak intensity simultaneously. Solar maximum continues through the year, bringing enhanced space weather risks. Megaconstellations reach critical density thresholds as Amazon races to deploy Project Kuiper satellites. Artemis missions prepare to send astronauts beyond Earth's radiation protection. And somewhere in the darkness, asteroids we haven't yet discovered continue their ancient orbits, some of them on trajectories that could intersect with our planet. NASA cannot ignore these threats because the stakes extend beyond individual missions or satellites. They threaten humanity's entire space-based infrastructure, the foundation for global communications, weather forecasting, navigation, scientific research, and national security. They challenge our ability to expand beyond Earth, potentially confining humanity to a single fragile world. Most critically, they demand coordinated international response, yet they emerge during a period of geopolitical tension when cooperation proves increasingly difficult. The solutions exist, at least in theory. Better detection systems, active debris removal, binding international regulations, advanced radiation shielding, improved space weather forecasting. But implementing these solutions requires sustained funding, political will, technological innovation, and diplomatic cooperation on unprecedented scales. The question facing NASA and the global space community in 2026 isn't whether these threats are real. The evidence is overwhelming. The question is whether humanity will respond with the urgency and unity these challenges demand before one or more of these threats transitions from potential danger to actual catastrophe. The cosmos has always been hostile to life. For billions of years, that hostility confined living things to the surface of a single planet. Now, as we venture beyond that surface, we're discovering that the void doesn't welcome visitors. Every satellite we launch, every mission we plan, every astronaut we send into space must navigate a gauntlet of natural and human-made hazards. NASA's engineers and scientists understand these threats with clarity, born from decades of study and harsh experience. The real test in 2026 and beyond will be whether the rest of us, citizens and leaders alike, grasp the dangers with sufficient clarity to support the solutions before it's too late. If this deep dive into the threats facing humanity's space endeavors has captured your attention, make sure to subscribe for more explorations into the challenges and opportunities shaping our future among the stars. The journey into space was never going to be easy, but understanding the obstacles is the first step toward overcoming them.